Hello everyone and welcome back to this next lecture in the DC-DC converter series, and this is where we had left off in the previous lecture where we were simulating the three-winding transformer. So we were extending the magnetic model of the two-winding transformer to add the third winding to the transformer. So for example, this is where we were editing the transformer.model.py file, which is the magnetic model of the transformer. So we will continue in this lecture with our changes. So as always, before I start the lecture, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length online courses on the MOOC website Udemy, which I'll be showing now. Instead of going to the MOOC website, I'm going to my own website, which is pythonpowerelectronics.com. So basically the name of the circuit simulator followed by .com, and this is the home page of the website. In this home page of the website, you can check out these 4 buttons, which describe more or less all the resources that you need to use this circuit simulator. So for example, there is download, there is learn, watch and read. Download is to download the circuit simulator files. Learn is to go to the online courses. Watch is the YouTube channel, and read other publications that I release with respect to the circuit simulator. So we will go to learn, which is the online courses, and here this is the list of the online courses which I have as of now. So I have 4 online courses, so I will just go through them. The very first online course is called Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python to simulate electrical circuits. So there is a little bit of brief background on power electronics. And finally, there is a case study of how to simulate a buck converter. And this course is hosted on Udemy. You can click on this button and go to the course link. And the next course is Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use Python to design filters and also use Python for basic signal processing tasks. So there is a bit of basic theory of signal processing, such as Laplace transform and the concept of filters, and finally there is a case study of how to design a low-pass filter and a notch filter using the Python packages. Again, this is hosted on Udemy. You can click on this button and go to the link. And the third course which I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to model magnetic components such as inductors, coupled transformers, coupled inductors and transformers. So there is a case study of how you can simulate a flyback converter which has multiple windings and is a high frequency transformer. Once again, the course is hosted on the MOOC website Udemy. And the latest course is Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python to design and analyze controllers for power electronic applications. So I use the case of a single phase grid connected converter in order to be able to analyze control systems as well as design controllers. So again, this is hosted on the MOOC website Udemy. So the link towards all these courses is provided in the description for this video. If you're interested, do check out the description of this video. So with this, I'll go back to my lecture. So in this lecture, this is where we had left off. Let's go back to the editor and let's continue. So we had started modifying the magnetic transformer, or rather the magnetic model or mathematical model of the transformer, and we were adding the third winding. So in many cases it's almost intuitive. We just have to add another third equation. So for example, in the cases where we are just looking at basic laws such as Faraday's law or Kirchhoff's voltage law, we just have to add the third equation and change the subscripts. The only place where we have to actually make substantial changes is in the equations for the flux linkages for each winding of the transformer, because now the flux linkage of each winding of the transformer will be dependent on the current in the third winding with respect to the mutual inductance of that winding and the third winding. So these are the equations we had written. There is only one change I need to make, and that is in the previous lecture I had taken the rated frequency of this transfer to be 1000 Hz. We will change this to 50 Hz because for now we are supplying winding 1 of the transformer with a 50 Hz AC voltage. So for now I will change this to 50 Hz. Right? Now keep going. We had also calculated several others. We had calculated the inductance, the leakage inductance, the mutual inductances, and several others. We are now going to continue with changing the magnetic model that will be solved iteratively during the simulation. So let's keep going. We are now at this stage calculating the induced EMF of the windings with respect to the voltage across the windings and the current provided by the windings. So all we have to do is replicate this equation for the third winding. That is all we have to do is change the subscripts. And after that, we are calculating the flux linkage of each winding as the integral of the induced EMF in that winding. And this also can be replicated for the third winding. Merely have to change the subscript of the winding. So these are basic laws. After this, we are now going to come to our flux linkages law. So we have already written these equations before. We can either add or we can just copy it from before. I'll just add that term. So as I said, the flux linkage of each winding will now contain, in addition to the other two windings, or rather the winding itself and winding 2, the current in winding 3 with respect to the mutual inductance between winding 1 and winding 3. Right? And I'll change this subscript as well. And the same goes for winding 2. So winding 2 is now M23 multiplied by I3. And with this we can add our flux linkage of winding 3. So again it is phi I3 psi 3 is equal to the self-inductance of winding 3 multiplied by the current in winding 3 and the mutual inductance between winding 1 and winding 3 and between winding 2 and winding 3. So you just have to change the subscript. So with this is our new set of equations. I'm going to delete all of this as we now have to rewrite these equations. Right? So let's just clean it up. Now the right way to solve this is by expressing these equations in a matrix form. So for example, what I should be doing is writing something like this. That is, these three flux linkages can be collected as a column vector. So when I say column vector, it means it is a matrix with three rows and one column. Right? So that's why it's called a column vector. And this can be expressed in terms of the inductance matrix. This is a square matrix with 3 rows and 3 columns. Remember, because we need to express all these. We need to express the self-inductance of the 3 windings as well as the mutual inductance between them. So therefore this is a square matrix, and this square matrix is multiplied by another column vector which is of the currents, these 3 currents. So this again is a column vector, which means it's a matrix with 3 rows and 1 column. Right? Now the correct way to do this is by solving such a matrix equation by converting L to an upper triangular form or a lower triangular form. So we can just say, I will just write upper or lower triangular form, and then solving the equations, or rather solving the equations to calculate the variables. Right? This is the correct way to do this. Why? Because this generic method can be applied to any transformer with any number of windings. So even if you have 10 windings, you can always express them in such a matrix form and you can solve them. Now in this lecture series, I will not be doing this because this solution requires several lectures, right? And I would rather focus on the actual forward transformer, or rather the transformer for the forward converter and later for the forward converter. So I do not want to go into this. If you want to know how this is done, that is how this matrix representation is done and how these equations are solved, just go over to this course, which is Simulation of Magnetics for Power Electronics using Python, in which I describe this process in detail. In this lecture, I will solve it manually. There's only one problem: a manual solution is going to be quite messy, right? So for here, since it's only a 3-winding transformer, it is acceptable. We could still manage. It's going to be messy, but we'll manage. So let's get started. So first, as always, we need to eliminate the currents and express them such that we can have one equation with only one variable. Because remember, we have 3 equations with 3 variables. So we have 3 simultaneous equations. So let's pick out the very first one. and copy it. Now what do we do? In this equation, let us express I1 in terms of I2 and I3. So for that, all we have to do, I'm just going to copy this, paste it again, and all I have to do is express this this current with respect to I1 and I2. So I'm going to take these two terms to the other side. So what that means is I'm going to copy this, paste it here, and since I'm taking it to the other side, I have to change the sign. And the same goes for here as well. I'm going to cut this out and paste it here, right? And as always, I have to change the sign because I'm taking it to the other side. So now that we have this, let me copy it and bring it over here. Now I'm going to cut this out, bring it to the left hand side because the idea is to express I1 in terms of these two. So let's bring it to the other side. Now, if I look at this, all I have to do is divide each term on the right hand side by L1. That's all I have to do, right? This expresses I1 in terms of I2 and I3, right? Now, this is just one equation. We need to do this for all the other equations as well. So let's keep going. This is psi I2. Now psi 2, or rather psi I2, psi 2 probably, psi 2 is expressed again in terms of all these three variables, right? What we need to do here is we need to again eliminate as many variables as possible. The good news is we have already calculated I1. So let us copy this again and paste it here, and let's copy this value of I1 that we've got and paste it here in this bracket. So all we're doing is we are substituting this value of I1, which we've expressed as I2 and I3, into this equation, right? So we've eliminated one variable. Now what that means is we can further expand, right? We can further expand. How do we expand? We just have to bring this term inside. So I'm going to just bring this term into each and every value. I think maybe I'm leaving too much space. And here as well. Right? So I've brought this M12 into each and every term. So I'm going to delete this here, right? And I'm going to open out this bracket. So we have brought this term into this equation, and we have now eliminated the variable I1 completely. So this equation is now only in terms of I2 and I3. So what that means is we can actually further expand. And what we can do is we can express I2 in terms of I3, right? So let's collect all the I2 terms and bring it to one side, and take all the other terms and take it to the other side, right? So let's start collecting. This is a term, this is a constant term, so take it to the other side and change the sign because we are taking it to the other side, right? And this term is I2, this term is I2, so they can stay where they are. Now let's take these two terms and move it to the other side. So first I'll cut this out, that is I3, and move it here. Again, we must change the sign since we are taking it to the other side. And the last term, also cut it out, paste it here, and as before, change the sign because we are taking it to the other side. So let's copy this and paste it. And as always, let's do this little change. Let's cut it out and bring it to the left hand side and delete it here. This is just rearranging. I'm just saying the left hand side is equal to the right hand side. Just shuffling them over, no difference. Now, what are we going to do? We are going to express this I2 in terms of I3, right? Again, I'm going to copy it as many times as you want, not a problem. And we have to now express I2, which means I need to take out this I2 as a common factor, right? I'm going to take this I2 out, remove it from here as well. And let me close the bracket. this is our expression. So all I have done is just taken out these common terms and brought I2 out. So now that I have this, we can express I2 in terms of I3. Let me cut this out and let me close this entire thing within a bracket and paste it. Okay. Of course, I need to put the divide by sign. Now that I have this, let's even further expand this out, right? And bring this within each and every term. So what I'm going to do, I'm going to take this, copy it here, copy it into the denominator here, and into the denominator here as well. And just divide it by this. Alright, and with this I can delete this. And the best part is I can just get rid of this outer bracket. And I have an equation where each term is pretty much independent. The advantage of this is it makes it slightly easier when you are solving them finally. Now we have I1 in terms of I2 and I3. We have expressed I2 in terms of I3. So an intermediate step is we can rewrite this equation of I1 and we can now replace this I2 term in here, right? Because remember, we have eliminated, we have expressed I1 in terms of I2 and I3. So we can express I1 also in terms of I3. So what that means is, here, let me copy this again. We have I2. All I have to do is open out this bracket and copy this entire term. As you can see, it's getting pretty messy, which is why I would say the recommended way to solve it is a matrix form. So we now have this equation. Again, we must expand it because in this form it's quite messy. So I'm just going to copy it again. And what I'm going to do is I'm going to open out these terms. So there is an M12 term here. I'm going to bring it in. Let me copy paste this and bring it in here. So this is M12 multiplied by psi I2. And remember, there is also divide by term. So I'm going to divide this also. So it's important that we are dividing it. So all we have to do is open out this bracket and just say L1 multiplied by. So basically we are taking into account both of these factors. And the same goes here. There is already an M12, so it becomes M12 squared. And here too, there is already an L1 term, so it's L1 squared. And here again, there is an M12 term multiplied again, so it's M12 squared. This is again multiplied by L1 again, so it's L1 squared. And there is a last very term, which is M12 multiplied by M23. And here again, we can multiply this entire thing by L1. So what I'm going to do is I'm going to say L1 multiplied by and open this bracket out again. So what this means is we have now opened out this bracket, which means we can delete this and delete the very last divide by L1. We don't need that because we brought this into each and every term. So this is now the expression of I1 in terms of I3, right? Now, as you can see, it's getting pretty messy, but we have now expressed I1 and I2 in terms of I3. Now this will be useful. Why? Because when we get to this equation of psi 3, we can express it in terms of I3 only. So let me just leave some space and copy it here. So this is the last equation. This last equation in terms of I3, I1 and I2. We have already expressed I1 and I2 in terms of I3. All we have to do is bring in these terms. So I3 can remain as it is, and here we can just delete this, put a parenthesis, copy this entire expression. Quite obviously, you see it's getting messy. And since it's already this long, I'm going to break it. Take this over to the next line. Put a comment. Just give a tab here so that we know what we're trying to do. And put a plus sign here. Actually, the plus sign was in the previous case. Yes, the plus sign was already there, so we don't need a plus sign here. So all I have to do is remove this I2, put a parenthesis, and copy this expression of I2 that we got before. So this is I2 in terms of I3, and of course the flux linkages. So this is now our expression. This is our expression of the flux linkage of winding 3 only with respect to the current in winding 3, and of course the flux linkages in the other windings as well, right? So what are we going to do? Here we need to again do a little bit of simplification because we need to calculate again. So let's go back here, copy this whole thing and bring it here. So what are we going to do? We need to start opening it out. Anytime you see this multiplied by sign, let's bring it in. So I'm going to leave a little bit of space so that I know what to delete. Multiply each and every term. It's a good thing we don't have to divide by anything, so that makes our life a little simpler. And the very last one, and this is it. So now that we are done with this, we can delete this bracket because we have accounted for this M13 in each and every term. So we can open it out, and here too we'll do the same. Just have to bring this into each and every term. No need to divide because we are only doing multiplication. And this is it. Again, we can get rid of this term because we've accounted for it. And this is all. So now that we have this, again, we need to take all these terms together. That is, we need to take the psi terms together, that is all the flux linkages together on one side, and take all the current terms on the other side. So what that means is, we cut these out wherever you see a psi, bring it to this side. And since we're bringing it to the other side, we must remember to change the sign. The same goes here. This is a psi term, cut it out, bring it to this side. Copy, paste, change the sign, keep going. There is another one, cut this out, bring it to this side. Again, remember to change the sign, keep going, and the remaining terms are all currents. So these can stay where they are. Let's look at this. We have again another term, cut it out, paste it here, and this is a positive, so we must remember to change the sign. And this is a psi term as well, cut it out, and bring it to this side, remember to change the sign. And is there any other term? I think that's it. So we have included all the terms that we could imagine on the left hand side, right? So what this means is, as always, this means we can now, as usual, perform our jugglery. That is, we're just going to take the left hand side and right hand side terms separately. So I'm just going to take all this cut it out, just paste it here for a minute, and what we need to do is we need take all these terms and put it on this side. So all I'm going to do is take it, that is put it on the left hand side, cut it out, paste it here, and cut these out as well. And paste it here. Some extra space. And all these are now equal to this new left hand side, right? So I'm just going to put the equal to sign here so that we know what we're doing. And copy everything past the equal to sign. So this is equal to this constant. That's what we are trying to get at. And now that we have this, all we have to do is calculate I3. This is one huge mess of an equation, but if you want to manually solve them, this is the only way. The only advantage is we can cover this in a single lecture. If I was to write the matrix equations, it might take 2 to 4 lectures, and I would rather not spend that much time on just solving equations, right? So now that we have this, all we have to do is solve, take these I3 terms out, right? Wherever you see an I3, take it out. And here as well, because these are all common factors. And this is it. All I have to do is open parenthesis, close parenthesis, multiply this entire thing by I3. And as always, one last step is I just have to, I'm not even sure if I want to write it. All I have to do is say I3 is equal to this right hand side term multiplied by this particular term, right? That's all I have to do. Well, I can just write it. What difference does it make? And let me just cut this out. This is I3. And now I'm going to bring this up here. This is the right hand side. Let me leave a little bit of space so that I know what I'm trying to divide by. And I'm going to paste this here. So this actually, probably there's another parenthesis, I can get rid of that. So now this is my final expression for I3. I can calculate I3 using the flux linkages, that is psi1, psi2, psi3, right? That is all these. I mean, there are different variations because we've of course calculated using different equations. Once we calculate I3, we can use this value of I3 in I1 and I2 to calculate the remaining two currents. And once we have the three currents, we can now calculate our new source, that is our winding voltages. So this is now the new magnetic model, right? As I said, it's a very, very messy equation, and this is what happens when you try to solve a lot of simultaneous equations manually. Always, whenever you have a lot of such simultaneous equations, use the matrix method of solving equations. Always. If you need to know about it, as I said, just check out this particular course in which I describe this in fairly great detail, right? With this, I will end this lecture. In the next lecture, we are going to then just complete the mathematical model and we will run the simulation. So, if you have any doubts about what I did, I would suggest that you take a piece of paper and just write these equations out yourself, or just verify this on your own. In the next lecture, we will simulate this, but if you have any doubts, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you in the next week's lecture. Thank you so much and see you soon. Goodbye for now.